Welcome to solverfy.
In this problem, we need to figure out what the pressure of chlorine is. We have a set of conditions, and I've written them down here. We know that the volume of this container is 15.5 liters. We know that the mass is 5.95 kilograms, but we won't actually need that. We need to know the number of moles that are in here. We know that the temperature is 225 degrees Celsius, and R, the gas constant, is 0.08206. And, well, constants tend to have weird units, but that's what it is. So, first, we're asked to find it according to the ideal gas law. PV equals nRT. But we are told only the mass. So we need to find out how many moles there are. So the way we can do that is first, we need to convert this to grams. So there should be 10 to the third grams per kilogram, which means we have 595 grams. I'll just erase this for now while we're figuring out the amount of moles. So from there, we need to find the molar weight. What we know is that for chlorine, the molar weight is 35.45 grams per mole, but we need the amount for CO2 because it is in a gaseous form and it's got two molecules. So instead, what we're going to find is that chlorine will have a molar weight of 70.90 grams per mole. So if we use this, we want moles, so we're going to put that on the top of our equation. Then we're going to put 70.90 grams per mole here. This will equal number of moles, which is 8.391 moles. To have space for this next part, I'll unfortunately delete all my work. So now we have all the info we need. We can look at the ideal gas law and solve for pressure. Under these circumstances, here I'm going to change colors again. PV equals nRT. We want to just get the pressure on one side. So let's say P equals nRT over volume. So I'm going to go ahead and write this out. We know that we have 8.391 moles times 0.08206 atmospheres liters over mole Kelvin. So lastly, we can't actually use this temperature. We have to convert it to Kelvin. So in this case, we just add 273.15. So the temperature will be 498.15 K. So hopefully they fix the error, but this is the temperature that's in the book. Our website right now says it has the wrong temperature. It says it's 2,225 degrees, which would be a lot. So we then times that by 498.5 Kelvin. Divide that by the volume, which is going to be 15.5 liters. So I'm not going to put this in a calculator, but when you do, you'll find that the answer is 22.13 atmospheres. So according to the ideal gas law, that is going to be the pressure within this container. There's a caveat. No gas is truly an ideal gas. And this is also true of chlorine. So we're going to be looking at the van der Waals equation, which is just a nice big modification of the ideal gas law. It takes into account the interparticle attractions and the volume of the actual particles themselves. To have them to work, I'll just go and keep erasing. So van der Waals equation is not much different, but it is a little longer. Almost there. So the equation in this case is going to be parentheses plus n squared A over mole squared times V minus NB. Just fix that. Equals nRT. So these stay the same. The idea is that this part of the... Why did I write moles? Excuse me. I meant to write over V squared. So this portion of the equation will account for the interparticle interactions and the effect they have on the pressure. And this portion will account for the volume of the actual particles, because we assume with ideal gases that they don't have a mass and don't really have a volume either. So what's important also in this equation is A and B. So these are constants that vary according to the gas. So in your book, you'll find in table 5.4, it actually has what these are. If you look there for chlorine, you'll see that A is 6.49 atmospheres times liter squared or mole squared. And B is going to be 0.0562 liters per mole. I'm not good at writing sixes. So these are the constants for chlorine gas. Now in this equation, once again, we're going to isolate P. So we'll take this and put it to the next side. So P plus n squared A over V squared equals nRT over V minus NB. So P will equal nRT over V minus NB, and we've now taken this, subtracted it from both sides. So we're going to say minus n squared A over V squared. I don't have a ton of room left, so I'm just going to scroll in. If my computer will let me. It won't. So rather than write out everything, if you plugged everything in right and you do all that, you'll find that PVDW is 20.92 atmospheres. So what we see is that van der Waals has adjusted, and the pressure is actually a little lower for chlorine than in real life, well, in this model, I should say, than it would be for an ideal gas. Thanks for listening. Hope this helped all of you.